Good, good evening, everyone in Saudi Arabia, and I guess also in London.
Yeah.
And thank you all for joining us today in this seminar. Um, Before starting, let me first acknowledge Air Products for sponsoring our hydrogen mobility concentration students. I would like also to thank KFUPM, American Institute of Chemical Engineering student chapter, and the Young Professional Committee of the Saudi Arabian section of AICHE for co-organizing this seminar with us. Today, we actually have a very distinguished speaker from Imperial College London. He is Professor Christos Morkidis, who is the Professor of Clean Energy Technologies in Imperial College. He also heads the Clean Energy Processes Lab, as well as the Experimental Multi-Phase Flow Lab in Imperial College. As many of you know, he is also the editor-in-chief of Applied Thermal Engineering, one of the top Q1 journals in the field. He specializes in thermodynamics and its application to thermal energy storage, recovery, and utilization processes, especially the application of solar energy and waste heat recovery for heating, cooling, and power generation purposes. He received the Imperial College President's Award for Research Excellence in 2017. He also won the Institution of Chemical Engineers Global Award for the Best Research Project in 2018. He also won the Institution of Mechanical Engineers Outstanding Paper Prize in 2016. And finally, recently, he won the Engineers Without Borders Chill Challenge recently in 2020. And before I leave the floor for our very distinguished speaker, let me first, in front of you all, thank him for being understanding and kind during a confusion that happened during the preparation of this seminar. But he was generous enough to resolve the conflict or the issue with us. So again, thank you so much, Professor, and we apologize for the confusion in the preparation. And I'll leave the floor for you. So you can start, Professor.
Thank you. Thank you very much. I wanted to say, first of all, before I start, really, it's a pleasure for me to have these discussions because, our work is all about developing technologies, pushing the boundaries of science and engineering and, having an opportunity to tell you about some of the things we're doing. And to maybe get your questions is really a joy for me, right? So, and no problem at all with the confusion with the time. That's really not an issue. It was very easy for us to resolve. Thank you for inviting me. It's a real pleasure. I visited KFUPM earlier this year, and I had a fantastic time there. So immediately when you asked me to present, I have a sort of a warm feeling for my time in Saudi Arabia. I had a great time there, very hospitable, and so it's a pleasure for me. And I want to try to tell you something in the next 45, 50 minutes, and I'll try to leave 10 minutes at the end or so for any questions or discussion or anything you want to clarify. Okay, so I'm going to jump right in. I think the title says it all. We're going to talk about how can we convert solar energy to useful energy vectors that people need, right? And generally by distributed applications, we really mean, that we're not talking about power stations here, right? So we're talking about smaller systems that can provide energy to homes, communities, neighborhoods, and we have to think of the problem holistically, right? So people need heating, if you're Saudi Arabia, cooling, power, clean water. So how can we use solar systems to provide this? That's really the point of today. So very quickly, I have like 2 or 3 slides for those of you who don't know our team, because I'm not one person doing all of this. Really, it's a big team of people and that I have a pleasure working with. And I'm trying to give you the flavor here, right? So our team is for about 40 people, PhD students, researchers, professionals, postdocs. And we try to cover the whole range of things from molecules, right? So how do you design the right materials? How do you design the right fluids? All the way up to system level optimization, technologies, fundamental processes, heat transfer, thermodynamics, and so on. So it's quite wide. We try to cover as much of it as possible. Of course, we're not experts in everything, right? So where we need to work with people, we collaborate. Okay, and this is a Department of Chemical Engineering where we're based in at South Kensington at Imperial. And I should say the focus of our work is technologies, right? It's the sort of the red circle. So this slide is kind of trying to tell you a little bit about how I see how we fit right into what's going on nowadays in research. So we look at technologies, but of course technologies have a certain performance, and that performance is governed by the processes within that are happening within those technologies, right? So you need to understand the fundamentals if you want to design better technologies. And of course technologies sit inside systems, right? So they interface with users that want things from these technologies. And so you can never really understand the true potential of some technology unless you put it in its application and try to understand how it operates within the system. So we need to talk right across scales to people who are doing fundamentals, to people who are looking at policy and how technologies are used by people within systems and so on. So our group, if you like, the CP laboratory has a number of divisions, as you can imagine, because we cover a lot of ground. As I said, we go from processes. So we have people that look at either mass transfer processes and intensification enhancement. We look at multi-phase flows because you have boiling and condensation of different types of fluids inside the processes that we care about, all the way to the energy division, which sort of looks at technologies and systems. Today, really, I think I'm going to just use my cursor here. Today, I'm really just sort of talking about things which are happening inside the energy technology part of the group. There are, of course, many other things that I don't have really time to go into, but that's where this talk sits. So I always start these discussions in solar energy by showing basically two slides, right? And I use this term, the cost delusion, all right? And the first slide is that you will hear from many people that renewable energy is expensive, right? It's expensive, and fossil fuels are cheap. Of course, this statement, it depends, right? I mean, it depends where you are in the world. If you're somewhere where oil and gas is cheap, then okay, that statement is true. But if this is the case of the US, and even in the UK, it's a similar picture. If you look at some other countries, right, basically what you can see here is something called the unsubsidized. Be careful, right? So this is not, some people say, oh yeah, it's cheap, but it's only because it's subsidized by the government. This is unsubsidized, right? Levelized cost. So the levelized cost, basically all the cost throughout, from the beginning of the plant to install it, to build it, to commission it, and to operate it over its lifetime, okay? And so basically green is everything alternative and blue is everything conventional. So in green, you'll see things like solar PV, right? Solar thermal, CSP, all these kind of things that you're familiar with. We call them renewable and sustainable energy technologies. And then in conventional, you find things like nuclear, right? You'll find things like internal combustion engines, and so on and so forth, right? And I challenge you to look at the chart, right? And tell me that the green costs, right, are fundamentally much higher than the blue costs, right? This is no longer true, right? This is not a true statement, and there is evidence, and the evidence is everywhere you look, that nowadays, right, the cost of renewables is basically so low that it's competitive with fossil fuel plants, right? It doesn't mean that this is true everywhere, of course, right? But if you're in the right place, you can see this picture, okay? Now, it's not that the people who are saying that are lying. Of course, it's not that they're lying. It's just that things have changed so quickly, right? 10 years ago, so you can see a plot here that starts at 2009. So roughly 10 years ago, right? You can see here the costs of things like, solar and wind were much higher than the cost of things like coal, which is the gray one, or nuclear, which is the purple one, right? So you can see here the dark blue one, which is like this utility scale solar, right? It's skyrocketing, it's up here, right? So someone, could tell you, yeah, but renewable technology solar is very expensive, and they were right? But what happened? Well, what happened is that nuclear and conventional technology has either stayed constant or gone up. But renewables, the costs have actually plummeted in 10 years' time. Look what's going on here, right? I don't need to convince you. You just need to look at the plots. And so that's exactly what explains this kind of seeming contradiction that some people might say it's very expensive. And the answer is yes, it was, but not anymore, okay? Now, when we say solar, what do we mean? Well, there are two types of solar, and I'm showing this on the slide on the right-hand side. You can have something called concentrated solar power, which is basically mirrors, which are focusing sunlight. And then you drive a power cycle to generate electricity. And the power cycle is it's conventional steam power plant, right? Just like you have coal, right? And then there's photovoltaics, which is very different. In photovoltaics, you're not boiling anything and running it through a turbine. So there are two very, very different technologies. And I want you to focus basically on these plots here, which are solar PV, and which compare the cost. This is the cost, right, of solar PV and CSP. This kind of the two alternatives that I showed you. You can see there where they're pointing. And again, you can see a number of things, right, which are how quickly the costs have dropped, right? Look in 10 years, how the costs have dropped from more than 30 US dollar cents per kilowatt hour, right, to now a few cents, right? And the other thing to note is that these green bars, right, are where fossil fuels, right? These are the cost of fossil fuels. So now you can see these renewable costs, right, are either similar or even in some cases, right, in some projects, they're even lower cost than fossil fuels. So it's really quite amazing what has happened, okay? But I want you to keep this picture because, when we say solar, a lot of people think about this, right? A lot of people think about solar PV, right? But this is not just the only solar. And I want us to always keep solar CSP on the map because there are some projections, and I don't have the time to go into the details, but the Fraunhofer Institute is a very well-established, renowned institute in Germany, very well respected. And if you see at their projections here, what I'm showing on the bottom right-hand side of CSP, which is the red one, right? And PV, which is the yellow one, you can see how they predict that, yes, you can see now that PV is growing very, very rapidly. And we know this, right? I mean, PV is growing very, very rapidly, but they project that after 2040 and 2050, CSP is going to overtake PV. And there are reasons for this that have to do with storage and the stability of the grid. And I don't have time to go into it, but we should always keep CSP on the map. Basically, never in your head just conflate solar with PV. Solar can be a number of things, one of which is PV, okay? Now, I want to focus a little bit our talk because, when we talk about technologies, right, and especially solar technologies, depending on the concentrating technology, you can have very, very high temperatures, right? So if you do a lot of concentration, you can have 1,000-degree heat, right? Or you can have very low concentration systems where the temperature, so in a conventional solar thermal system in your home, you're not generating 1,000 degrees, right? You're generating maximum 100 degrees just to heat up some water. So there's a huge scale of temperatures that you can have. And there's also a huge range of scales that you can have. I said before, up here you'll have power stations, right? Tens of megawatts, 100 megawatts. And down here you'll have very small systems for a home, for a neighborhood. And we're focusing in this region, right? We're focusing on small systems at lower temperatures. Okay, we're not looking at power stations like this. This is distributed applications. So what options do we have? Well, we have a need, and I'm now discussing a little bit more heat and power. I'll come to the cooling part later, but people need heat and power in their homes, right? They need heat for hot water. They need heat to, if it's cold, they need to heat the home, so-called space heating. And they need electricity, right, to drive whatever electrical demands they have in their home. So how can we supply this with solar energy? Well, there are technologies that are dedicated for, right, to provide a thermal output, and they're called solar thermal collectors, right? So these are solar thermal collectors. You put them up on your roof and they can provide you with heating, right? And also there are dedicated technologies that can generate electricity, and we've just spoken about them, right? So you could have PV, right, like this one, or you could have these kind of CSP plants. They can be concentrating, so they could be CSP, or they could just be solar power where you don't concentrate them. That's also possible. So you have different technologies that can do any one of the two, right? And which are designed specifically to do that. But the real question is, can we have a system, right? Can we have a solar system where these two functions, so these two energy vectors, the thermal output and the electrical output, are coming from the same system? Yeah. And that says, of course, and also not just of course, but there are a number of options. One option is on the top right-hand side, and another option is on the bottom right-hand side. So one option is basically taking a solar thermal collector like this one, where you can generate heat at a relatively high temperature. By relatively, I don't mean 1,000 degrees, I mean even 100, 200 degrees. And you can use this heat to drive a thermodynamic power cycle. And this thermodynamic power cycle, generates electricity, right? But it also rejects heat. this is what happens with all power cycles, right? So if you go to any power station, you'll find that the power station has a chimney, right? It's not really a chimney. There's a chimney for the exhaust gases, that's separate, but it has this other um, cooling tower, it's called. And you can see some steam going up. Well, that's the cooling part, right? That's you need to cool a power station. So you always reject some heat. And so really what you're doing is you have this dual output, right, from the same plant. You can provide heat and you can provide electricity. But also you can have something called hybrid PV thermal collectors. And these hybrid PV thermal collectors are similar to PV collectors, but what you do is you now extract not just the electricity from the collector, but you also extract some heat. And my talk is really about this. Okay, so my talk today is about this. Now let's talk a little bit about, what's the point of this PVT, right? Not PV, but PVT collectors. Well, one thing you need to know about PV technology is that if you have a cell and you put it in an environment and it's a nice sunny day, very hot, right? That cell is going to get very hot too, right? If you put something in the sun, it heats up. And we know that the efficiency of PV cells, right, drops as the temperature increases. So what happens is on a really nice sunny day, you put your panel on the roof, and you think you're going to get all this power, and actually you do get a lot of power, but you have a massive loss because of the fact that it's quickly going to heat up, right? And when the manufacturer rates a panel and says this panel, right, is X watts, right? Really what they're telling you is how much power it generates at 25 degrees. And if you're not operating at 25 degrees and you're operating at 65, 75, and it's possible to run them that hot, right, on just a very sunny day, you can have a huge loss in efficiency of that panel, okay? So what can you do, right? I mean, what can you do? Basically, we're saying we have this line and we're operating very, very hot out here. Well, someone might say, well, it's easy, right? You just cool them down. So if you cool them down, you're moving from the right-hand side of this plot to the left, and you're gaining electrical efficiency. You're generating more and more and more electricity because you're cooling this thing down. And oh, by the way, but now, right, because I'm cooling this thing down, I'm pulling heat from the collector. Well, but now I have a thermal output because, that heat is now, I can deliver it to someone, right? And so here we are, right? We have these types of collectors, and you can see here, you can have unglazed designs. Really, unglazed designs means that there's no glass cover on top of the panel. So you can see the cells here, there's a PV module, and underneath, we have a structure that removes heat. So there's a flow of water through here, and it cools the back of the cell. So it removes heat and it heats the water, right? So we have these types of designs, commercial technology. And we have glazed designs where the same thing happens, but you can see a blow up here where you have the channels underneath where you pass some kind of water and you cool the cells, and then on top of the cells, you have a glazing layer. Right now, you could say, well, why are you adding this glazing layer? I'll come back to it later. There are advantages for doing that. But let's have a look very quickly, right, at the thermal output and electrical output. You can look at this in the same way as you would see the electrical efficiency and the thermal efficiency of these commercial PVT collectors, right? And I want to, there are different types of designs, and I want you to just focus on the red dots on this figure. Okay, so if you look at the red dots, what you see is that there's an inverse correlation, right? So designs that tend to have a good electrical efficiency, so you come down here, these ones have a poor thermal efficiency. And designs that have a poor thermal efficiency, they lose on their electrical efficiency. Do you see that? Right? There's a negative correlation. Why does that happen, right? Well, it's actually quite simple for me to explain, and it's a little bit here on the right-hand side, but effectively what happens is, as you try to trap, if you want something which is very good in terms of its thermal performance, you want to try to trap, right, as much heat into the collector as possible. But the more heat you trap, the more you're penalizing your electrical efficiency, right? Because remember before, right, the hotter something gets, yeah, the worse its electrical performance is from the PV side. So you always end up with this sort of trade-off where you can't get both. You can't be both thermally good, right, and electrically good. You can say, well, okay, I can sacrifice a little bit of my thermal efficiency because I really want to be electrically efficient, or vice versa. You can sacrifice a little bit of my electrical efficiency because I want to be really thermally efficient, but you can't have both. And of course, that begs the question, right? What's the point of all of this? And of course, with electricity, the output doesn't really matter, but with heat, it really does matter. So if you are thermally efficient, what you're able to do is you are able to generate high temperatures without losses. Yeah. So what this means is that you have a more useful ability to do more things the higher the temperature that you have in your output. And you can see in this slide what I'm trying to say, right? So if you have very low temperature heat, you can only do pool heating or space heating. If you have very high temperature heat, you can do that, plus a whole lot of other things that provide heat for industrial processes and so on. Okay, so let's now think about what we've just said and see, okay, what is our, how can we build a high performance collector? In some sense, what I'm trying to say is, okay, how can we think about this problem of getting a high efficiency, high electrical efficiency, high thermal efficiency? Well, high efficiency really means low loss, isn't it? Because basically the efficiency is the useful output from your collector, right? Which means the less you lose from the collector, the more useful output you're going to have. So we can think about basically minimizing heat losses. And what are those heat losses? Well, there are two mechanisms of heat transfer in a PVT collector, in fact, any collector. And one is through basically radiation, and one is through convection, right? So you lose heat radiatively here, and you can lose heat by convection to the air which is sitting above your collector, right? So if your collector gets hot, thermal plumes are going to rise and remove heat, and also it's going to radiate heat. And of course, the question then is, well, okay, fine. If I identify those heat losses, can I reduce them? And if I reduce them, won't my efficiency go up? And the question is, well, yes, of course, that's exactly what we try to do, right? So we try to say, okay, we have these two mechanisms. We can lose heat by convection. We can lose heat by radiation. How can we reduce those vectors of lost energy? How can we suppress these heat losses? And well, of course, you can put a glazing layer here, and you can pull a vacuum. So that reduces convective losses, because convection is very weak inside a vacuum. It doesn't cut the radiation down, but it cuts the convection down. And is there anything we can do about radiation? And the answer is, well, yes, of course, because radiation is a function of the emissivity of a material. So if we find a material or a coating that has a low emissivity, then we can also suppress the radiation from the surface, okay? And so we've been looking at exactly this, right? We'll be looking at this issue of how can we coat, right, PV panels with materials that can suppress losses. It's a little bit more complicated than I said, because in reality, what you want to do is you want to absorb the sunlight and you want to suppress losses, which introduce actually a little bit of a complexity in terms of exactly what you're trying to do to the emissivity. And I don't have time to go into the details, unfortunately, but I think the main lesson to take away from this slide is that if we select a suitable coating, right, then we are able, right, to optimize the radiative performance of our collector, right, and to trap as much sunlight as we can, and to stop some of the radiation, which allows us to increase the efficiency of the collector. And this is exactly what you're seeing here, right? So here we're on the roof of chemical engineering, and you can see a PVT collector design that we've been doing some tests on. And you can see inside there are two collectors. You can see that there's a tube and there's a vacuum inside. So that's your vacuum insulation that's reducing convective losses. And inside the tube, you can also see that we have these cells, and you can see that the color of the cell is different from between the left and the right. And that's because on the left, we've added a coating, which is a low emissivity coating, to suppress the radiation from the tube on the left-hand side. So this is a specific, let's say, engineering design or solution to improving efficiency. Now, so far, I've basically been focusing on collectors, which are so-called, I call them conventional collectors, right? Which are sort of similar to what I showed you before. You have a PV cell, and behind the PV cell, you have some kind of fluid, and the fluid is flowing as a coolant, right? So it's pulling out heat from the cell, and it's reducing the cell's temperature. But there's another very interesting type of solution, which is a little bit more, is a little bit newer than what I described before, which is called spectral splitting. Okay, now spectral splitting relies on the fact that cells, right, so PV cells are not sensitive, right, so cannot convert all of the sunlight to useful electricity. So they can only convert part of it. If you look at, for example, gallium arsenide, which is this purple one over here, right? This plot basically shows you that if you have sunlight between these wavelengths, right, then this cell can convert that sunlight to electricity. Not all of it, but it can convert it to electricity. But if you have sunlight which is above this wavelength, then it has zero ability to convert it to electricity, right? So what we're saying is if the sunlight is coming up and there's a distribution over different colors and wavelengths, right? Then for this particular cell, only this part of the spectrum up to here of the sunlight, right, can be converted to electricity. And anything higher, right, well, what's going to happen to it? Is it not going to be absorbed? Of course it's going to be absorbed. It's going to be absorbed. It's going to heat up the cell, but it's not going to be converted to electricity. So the question is, right, really the motivation here is, why would you want to send that part of the sunlight to the cell in the first place? All it's going to do is it's going to end up heating it, right? So we don't. And there are a number of designs, right? Different people looking at different things. We also have a spin-out company from our department looking at a particular solution to this. And in fact, we've submitted recently a proposal with KFUPM to explore this in a Saudi Arabian climate, our own particular solution to this problem of, okay, how can we split the sunlight, right? So that the not useful part just gets sent away from the cell, right, to become heat, and only the useful part gets sent to the cell to be converted to electricity, right? That way we're heating up the cell less, right? And this is one way to basically generate both electricity and heat with a higher efficiency than you would if you sent everything to the cell in the first place. And so here, this is what you're trying to do. This is some simulations we run for our technology, and you can find this on our website. But ideally, this is what you're looking for. You're looking for, so here you're seeing, so a PV, right, has a particular efficiency. And a PVT, what tends to happen is you can trap some of the heat. So now you have so in a conventional PVT, you're trapping some of the heat, but because of the fact that you're trapping it, you're paying an electricity penalty, right? That's the problem, that you're always trading off, right? To get the heat, you're losing electricity. And what we're trying to do is we're trying to get the heat, but without penalizing the electricity, right? And that's some simulations that we were running to prove that our concept can have this type of benefit. So in terms of technology development, how do we proceed, right? How do we say, oh, we have a nice concept, right? Maybe we can do this or maybe we can do that, but how do we do it in practice? How do we go from there to an actual system where we say, oh, this is so much better than something else? Well, we start at the smallest unit. We'll start from the cell. We have a cell. Maybe we have an idea about how to coat this cell with a new material, right? So we can characterize, right, the cell performance itself. And we can say, for example, okay, we can now modify the emissivity of this cell. We can then take those cells, right, and we can put them on a PVT collector. And initially, we always do tests indoors in something called a solar simulator. So a solar simulator is, you don't take something and you go straight outdoors because there are too many variables. But a solar simulator is an instrument that basically gives you a very well-defined and constant solar spectrum, right, that you can then check your particular design on. And here we can verify, for example, right, that we can gain in efficiency, right, without necessarily having electrical losses, right, so electricity losses. Now, in this type of design, you have multiple approaches, and we do both, right? You attack it from a modeling perspective, right? So you start modeling things in 3D, right? Dynamic models. We use things like COMSOL and other types of modeling tools to design our collectors and to optimize them. Okay, there are different types of designs you can imagine, right? So this is called a sheet and tube design. This is called a flat box design. There are many, many different types of designs. But what I'm trying to say is, at the collector model, you can model it, number one, and simulate its performance. And of course, then the final step is you need to go outdoors, right? And you need to do the actual testing, right? So you're never going to convince someone if all you have is modeling, even if it's 3D and dynamic and up and down, right? And we've chosen two particular climates to do tests at. We have tests in London, which is representative of a northern climate, so small irradiance, low temperatures, right? And Limassol, which is basically where I come from, and not that far away from Saudi Arabia, actually. So, very hot, sunny, 40, 45 degrees in the summer and quite sunny, right? So we were trying to do tests of very different weather conditions. And this is the sort of lab that we have in Cyprus for testing in collaboration with a colleague of mine on the right-hand side. On the left-hand side, sorry, so Cyprus is this bit here on the top. And this bit here on the bottom was the picture that I showed you about before as well, which is basically our measuring station in the UK. You can already see that the UK picture is a bit grayer than the one in Cyprus. But what I'm trying to say is that we have these testing facilities where we can test our collectors. And of course, one of the major things that happen, right, that happens in real climates, right, is that unlike in a model where you say, oh, the sun goes up and comes down, right, in reality, you have something like this. Yeah, so this is a real weather condition, and your system and your collector has to respond to this, right? This is the real weather, the real solar incident sunlight hitting the collector, not this, right? And if you really want to try to predict how your system would perform in this case, the problem gets very, very complicated, because you don't only need to understand how the system performs in so-called steady state, but you also need to understand the transience of the system. So that means how quickly can the system go from one operating point to another operating point. And there are very specific types of characterization tests that we do for different types of designs, collectors, whether we have the evacuated tube design or flat plate designs. There are different types of designs, and have very different, let's say, response times, right? So some respond very quickly, right, to the weather, and some are very slow, okay? And this is very important in determining how these collectors will respond in a real environment outdoors, okay? And I'm showing here a particular day, and I'm showing what happens. So, so what I'm saying is the irradiance on a particular day was going up and down. So this is just us measuring the solar incident irradiance, right? And here we have different types of models, right? In which in some cases we account for the dynamics, the sort of transient performance of the system, and in other cases we neglect it, right? And you can see that in some cases, if you're not careful, you could be up to 40% wrong, right? So you could be getting a factor of 2 a prediction wrong, simply because you ignored something that would be happening in a real environment. So it's very important, right, to do proper simulations and to account for things. And of course, in the end of the day, right, we've spoken a lot about the cells and then the collectors. And we said the collectors, we can model them, we can test them, right? But actually that's not even the end of it, because then you need to have that collector inside the system, right? So usually the collector, you connect it with pipes to a tank, right? And the tank gets heated up during the day, and there's a user which is interfacing with this. So there's a whole system, let's call it, right? And we need to try to understand, okay, what is the system capable of? Not just the performance, but in some cases, ultimately also the cost, right? How much does it cost? And is it better than something else? And so this part of my presentation, I'm going to go a little bit faster, but it's just a flavor, right, of, okay, what happens when we start considering PVT technology, which is able to co-generate heat and electricity in different systems and for different applications, right? The point isn't the details, but the point is to kind of give you a flavor for, okay, what type of problems are we looking at? Okay. And so you can see things here. You can have many, many, many different configurations, right? You can have your solar collector, and on the thermal side, you could be driving power cycles. You could be storing heat for hot water purposes. You could be driving cooling cycles, which are thermally powered. You could be doing many, many things, and there are many different ways to connect these systems. And this is a little bit more of a generic picture. And then you could have whole control systems, which, in some applications, the electricity price, for example, varies from time to time. So you can have whole dynamic controllers that say store, right, solar energy at a time when the electricity price is cheap. And then as soon as the electricity becomes very expensive, right, you don't want to import the electricity from the grid because you're paying a lot of money. So you just delay, right, the generation of electricity to a later time when the electricity is very expensive. So you have all of these complicated things going on, very complicated systems with multiple, control issues that respond to the weather, that respond to price signals, and of course, ultimately, right, deliver useful energy vectors to some end user. And we've looked at things like, okay, how would you design these systems, right, for different households and different weather conditions? So you can imagine that, going to different countries, you don't only have different weather conditions, but you also, the different weather conditions also mean that you have different demands for energy, right? So if I go to Finland, right, they don't need a lot of cooling, you can imagine, but they need space heating. And if I go to Saudi Arabia, they don't need a lot of heating, but they need a lot of cooling. So depending on where you are, it's not just the weather conditions in terms of the solar irradiance changes, but also the demands of the end users change. So it's interesting to look at, okay, how would these systems perform in different climates? And we've done a lot of studies. Was a study that I'm showing here where we focused on the European Union, going all the way from Helsinki, right, all the way down to Seville, right? Very, very different weather conditions, trying to find, okay, given a certain fraction of some roof of some household that you fill, what fraction of the energy demand of that household can you cover, right? So you can cover 60% of this and 30% of that and 100% of the cooling or whatever, okay? You can go to slightly bigger systems. You can say, okay, I'm not just interested in homes, right? But I could go to sort of commercial or larger, right? Community systems. Here we have, how can we heat a swimming pool, right? And generate electricity to run the pumps and everything, right? In a sports center in Bari, we went, we got the drawings, we got the energy demands from the sports center, and we tried to say, okay, so if we cover the available area, what is our capacity to, right, cover the demands for heating and cooling for the, there's an indoor swimming pool and an outdoor swimming pool, and so on and so forth. And you can run simulations over the course of a whole year, right? Time varying simulations, the weather is changing day to day, right? And you can find, for example, okay, of all of the heat that I require over the course of a year for my swimming pool, I can cover 60%, right, by installing this system over the available roof space. I can't get any more because I don't have any more area available to me. I can get less. And of course, equivalently, right? How much of the electricity that I'm consuming can I cover? How much of the, right, other vectors that I don't have a lot of time to get into, can I generate from this particular system? I spoke very briefly about spectral splitting systems. So study 1 and 2 was really more conventional systems. Here we start, okay, now what would be, right, the potential of a spectral splitting system in this type of larger scale in semi-industrial application? Here we have a dairy farm. In dairy farms, there's a lot of demand for medium temperature heat, right? And of course, a lot of electricity as well. And so here's us kind of designing a system and trying to say, okay, if you install a certain area in a dairy farm, what fraction of different types of demands can we cover, right? So you can come up with some fraction of the demand for that particular case study that we were looking at. And these are significant reductions, right? What this really means for an end user is that if you were generating steam, let's say by burning oil, right? You're now burning 80% less oil. So only 20% of what it was before, and so on and so forth, of course, at a cost, right? So all of this has to come together economically as well. And this is what this is showing. Unfortunately, I don't have time to go into all of the details, but I wanted to give you a flavor, right, that we need to consider cost. And there are many, many different types of cost in economic indicators that we consider. So here we have something called a payback time, which is how long does it take before this system pays back the investment? And you can see here, right, that if you design it carefully, and this parameter here that I don't have time to get into is quite small, then you can have payback times 12 years. Right? But if something is very expensive, it could go right above 25 years. That's an important economic indicator, is payback time. But there's also something called a levelized cost of energy. And again, you want this levelized cost to be as low as possible. Okay, we then can have even more complicated systems, just to give you a flavor again, because before we were talking about solar energy, but there was only a solar energy input. That's not necessary. You might have a hybrid renewable energy system where you have sunlight, right? But you also have a wind turbine as part of this grid, right? And you also have a biomass boiler, right? So you can get heat from your biomass boiler. Biomass is a renewable source of heat. Wind, of course, and solar are both renewable forms of energy. And so you can start, right, balancing the different parts of the system to generate electricity or heat or whatever, right? So this can be many very, very complicated systems. And unfortunately, again, I don't want to go into the details. I'm not trying to kind of confuse you. I'm just trying to say, you can have very complex systems, and you can look at different types of systems. You can look at systems that have, let's say, PV panels, right? And a biomass boiler. WT is a wind turbine, right? So that's one type of hybrid renewable system. So you have the solar, wind, right, and biomass. But instead of solar PV, you might have a solar evacuated tube collector. So this is just generating a thermal, right? So heat, hot water. Or you might have a PVT system. So this is solar to heat and electricity plus the wind turbines and the boilers. And you can look at, right, how much energy can I generate? over different months of the year, and how much of the fraction, right, of a particular end user can I cover. In this case, what we're looking at here is a hotel in Egypt. So actually very, very close to you. So these are the energy demands of a hotel in Egypt, and you can see, right, over the different months how it changes, and you can see the different solutions, and that some are better electrically, some are better thermally, and some are a bit of a mix of both. Okay, I'll jump this very quickly, and I'll jump that very quickly. Now, we spoke a lot about heat and electricity. I want to talk a little bit about cooling, and I want to talk about a technology that we're looking at called the diffusion absorption refrigerator. This technology was the technology that we won the, the chill challenge with. And it's basically a way to go directly from solar energy. I know this is very complicated, and my intention wasn't to confuse you, but it's a way to go directly from a heat source, right? Here and here, to generating a cooling effect. And you can see there's no, what's interesting here is that there's no electricity consumption in the system. So this is not like a sort of a vapor compression system where you have a compressor, you have an air conditioning system, you plug it into the grid, you pull electricity, right, and you generate a cooling effect. This is basically generating a cooling without any access to electricity. And you can see it here, what it looks like. We're working with a company called Solar Polar to develop this technology, and it's basically an off-grid cooling system. We're doing tests indoors. You can see here the DAR unit. It generates maybe up to about 100 at the moment, maybe 100 to 200 watts of cooling per unit. You can of course put them modular and put a number of them in parallel, and of course, during the testing we can test for different conditions, right? How much cooling can you get, what's the COP, etc., etc. And here's some outdoor testing that we do, right? So indoor testing, remember, and then outdoor testing, so we can connect our DAR unit, in this case, to some evacuated tube collectors that supply heat to run this to give you a cooling effect. Okay, there are ways, and again, I'm not going to go into details, similar to what I did here. Just like there are ways to take the heat that is generated by a PVT collector and to convert that to cooling, there are also ways to take that heat and generate an additional amount of electricity, right? So what I'm saying here is if you have a PVT system, that's generating electricity, right? But it's also generating heat. And what we're saying here is that, but part of that heat can also become additional electricity, so a secondary electricity. And there are technologies that can generate heat from lower temperature sources, right? So let's say down to about 100 degrees, and they're called organic Rankine cycles. I don't have time to tell you about them, but they're suitable for converting low temperature heat to electricity. There's a lot of interest, right, in ORC technology. You can see here how quickly, right, the installed capacity and how the market of ORC systems has grown. This is the global market and how many plants exist. There's a huge academic research also interest in this particular technology. Okay, and the basics are really things that this type of technology is really just the same as a steam power station, right? So in a power station, what you do is you burn something, you have high temperature heat, and you use it to boil steam and to drive a turbine, right? That's what really happens in a conventional power stations. And basically, this is exactly the same as that, only instead of boiling heat, you're boiling a different fluid, which happens to be an organic fluid, and that's why it's called an organic Rankine cycle, as opposed to just a Rankine cycle, which is your conventional power station that you're aware of. There's a lot of research that goes into this, but I think the main point of this slide is just kind of show you that because of the fact that you can use these organic fluids instead of steam, it allows you, right, to operate. So this is the boiling process, right? And it allows you to boil something you can see here at low temperatures. And this is exactly the property of this type of cycle, right? Which makes it possible for you to convert lower temperature heat than, let's say, steam, okay, to electricity efficiently. There are many types of system, again, with storage, with thermal energy storage, right? You can connect it, you can recover some of the heat as well for heat provision. It can get very complicated, okay? But I wanted to just say that there are things called, right, solar ORC systems, where you take the heat from a thermal collector or a PV thermal collector, both have a thermal output, and you convert that, right, to an amount of useful electricity. And there's a cost associated with that, and we have to look at all of these things, right? We have to look at how much, what is the potential, given a certain area for you to generate, right, some amount of electricity, is that useful, and at what cost does this come? And of course, the final thing is control, right? So you don't just have a system that passively responds to the sun. The sun goes up, let's generate electricity. The sun goes down, let's not generate electricity, right? You can have control by which you have storage, right? And during the day when electricity is cheap, right, you might want to be storing something. So you see what's happening here. This is our store and the energy that's being stored. And during the day, we're storing the energy. And then at 5 p.m. here, right, you know how the British love to have a cup of tea, right, at 5 o'clock. And so everybody switches on the kettle at the same time at 5 p.m. And what happens is that because everybody wants electricity at the same time, the price of the electricity goes up. Yeah. And so what we're doing here in this household, right, which is modeled in the UK climate, right, it's a solar ORC system in the UK climate, is we store energy, and instead of buying electricity from the grid at 5 p.m., we basically discharge our store, right, starting at 5 p.m. and it goes until about 9, 10, or 11. It depends on the size of the store and the material and how much storage capacity you have and all of these things. But anyway, the point is you discharge it at the time of the day that you want. So you can play all of these games with controlling the system using the energy at the point and the time that you need it. I'm going to skip that. And I'm going to skip that because I mentioned that you can go from, this is the efficiency. Okay, maybe I just leave it. This is the efficiency with which you can convert sunlight to electricity with a solar ORC system, right? So it's basically between 5 and 6%. It might sound low relative to PV. So PV, you'd get something like, say, 3 times this, right? It might sound low, but actually this is also a little bit cheaper than PV. So there's that sort of competition there. Okay, there are also larger scale systems. My talk isn't really about this, but I wanted us to keep right in the back of our minds that all of the things that I said, just because in our talk we said, okay, let's focus on small scale system and people's homes and what can we do in these kind of distributed applications, doesn't mean that you can't apply them in huge power stations, right? I mean, you can do it. And again, you have issues about cost and all of these things, right? And what's the best configuration and the best technology and optimizing the system and so on and so forth, and what's the best way to operate it and control it. So all of these things exist, and they exist just like in the small scale systems we discussed. They also exist in the large scale systems. I just don't have time to go into today. So I have, I think, 2 or 3 slides left, which are just some very quick comments from us or from me about, okay, what are we working on at the moment? I mentioned that, we have a personal interest through a spin-out company in PVT technology, right? So PVT collectors. We're specifically looking at a number of different concepts, one of which is based on something called transparent photovoltaic. So you can see here, so it's not entirely clear, but basically this is a photovoltaic material through which you can see, right? And what we're trying to do is we're trying to maybe see whether you can use these semi-transparent, right, PV materials within a PVT collector. This hasn't been done before. As I said, there are many different concepts. This is just one of them, okay? So this kind of the use of transparent solar cells, PV cells, plus the heat recovery as part of a PVT collector to generate a thermal output, okay? So we're looking at different types of cells. I don't want you to look at the details of this. The main, let's say, takeaway from this slide is that, and it's difficult to see, so I need to kind of explain a little bit, that different spectral splitting designs and what materials you pick for the PV cell, right? Which material you pick for the filter, which is going to split the sunlight into the different parts that we mentioned before. So all of these design decisions, right, depend on your application, right? So if you're in an application where electricity is very expensive and very valuable, but heat is not, right? Naturally, you're going to want to design a collector which is going more towards efficient electricity production than heat, and vice versa, right? So if gas or if your thermal, right, energy is very expensive to generate, right, you want to prioritize that. So this can lead us to different designs in terms of, we're seeing here, these are very difficult figures to understand. I know that, but the main point I'm trying to make is that, we have many different types of cells here, right? So different cell will give a different performance, right? So how do I pick the right cell? And having picked the right cell, right? How do I pick the right filter to use? And the filter is that component of the PVT which splits the sunlight into different parts, right? Some of it's sent to the PV cell for electricity, some of it's sent somewhere else. And of course, it's outdoor testing, right? So we're up in the up in the roof. We're running tests, comparing. Do we get predictions that are like the ones that I show you initially? Do we not? How does it compare with the standard PV panel sitting next in the same conditions, same angle, same weather, right? Do we really get a benefit? Um, do we get some heat out, but we just kill the electricity of the PV, or do we have the same electricity generation as the PV, which is next to it, but now plus some heat, right? So these are tests which are ongoing. We have some evidence that, okay, our design kind of makes sense, but it's really very early stages. I think I'm just going to end it there. Again, these are results from the roof where we're kind of showing that you can get relative to a PV panel. So here's a PV panel, right? And you can get in some cases the same efficiency electrically plus some heat, right? If you design the collector carefully. So that's it from me. I didn't leave 10 minutes, I lied. I left 6 minutes. But I hope that I gave you a bit of a flavor of how do we attack technology development from the very small component to the collector to this whole system. How do we optimize the operation of the system, the control, the testing and all the testing, outdoor, indoor, modeling, all of the complexity and all of the things you need to think about, the right materials, the right cells, and all of the things that you could be doing with solar technology. And this is basically looking for technologies that are going to be available not now, but maybe in 5 years, in 10 years, right? And I really look forward to any questions you have, or I'll be very happy to discuss any of it with you. Thank you for your attention. Thank you very much.
Thank you, Professor Marquidis. That was really, really a very nice presentation.
Appreciate
Very
it.
interesting. Okay, so let's start with questions. Please, gentlemen, raise your hand and we will just call your name. Boker Agili? Go ahead, sir.
Yes, thank you. Thank you, Christos. Wonderful and great presentation and great work.
Thank you. Thank you very much.
The question is, I really missed part of the lecture. My name is Boker Agili. Okay, I missed part of the lecture, but I was really wondering if you discussed the regular PV systems with BVT in terms of efficiency and cost. Did you compare that? I did. Maybe I missed when I last portion of the lecture.
Yes. Okay. So that's a good point. In fact, actually, I'm going to start from I'm going to start from a slide that I had right at the beginning, and I'm going to say something quite quickly, and actually I'm going to jump back to the end in these last slides that I have. But so you're right. Yeah. There are different approaches to this problem. In my opinion, right, the approach is not one that should simply focus on performance, right? So it's not simply about 10%, I'm 10% and you're 12%, but it has to be, I'm 10% at this cost and you're 12% at this other cost. Now let's look at the numbers, which one is better, right? And so you can't really do this analysis fully without accounting for the costs. And I can tell you that in the work that we do, we not always, because there's usually a step, right? First of all, you sort of look at, okay, what's the technical performance of a system? And then, okay, I understand the technical potential. Now, what's the economic potential of the system? And then you iterate a little bit, right? Can I improve the economic potential of the system by making changes to the technical performance of the system, or reducing some cost of some component or whatever? So all of these things are done. But very quickly to answer your question, have we considered comparing PV, right, to PVT? And the answer is yes, of course, in multiple ways. On this particular slide, you can see how we're comparing just the technical, not the economic, but the technical performance of a PV system, which is, a PV system only has electricity, right? So blue is electricity. And this is a conventional PVT system. So you can see that the electricity from a PVT system, a conventional one, is lower, but of course you're generating some thermal energy, right? And here's a spectral splitting design, which is a particular sort of variant of PVT, so still PVT, where you do not sacrifice the electrical efficiency of the PV. So you have the same electrical efficiency, right? Plus heat. Okay, now, of course, we can talk about costs and all of those come in. And in some of the results that I was showing, right, where I was comparing PV-based systems with PVT-based systems, there was a cost down as well. So let me show you, for example, right here. You can see here a system, which is a hybrid system, so quite complicated, that involves PV driving heat pumps, right, to get heat, cooling, whatever, with PVT, right? And of course, you know, you're going to find that with PV systems you have more electricity. This is a conventional PVT, right? This is not spectral splitting. You have a bit more electricity but less heat, right? And of course there are economics. So you can see here comparisons. I'm showing you here. So a PV system and a PVT system. So the PVT system is more expensive, as you'd expect, because now you have all the hydraulics to deal with, not just the electricity, right? And the payback is a little bit lower for PV systems. You can see here, but it's not a million miles away. Okay?
Yeah.
And, yeah. So
I got it. So can I have follow-up question?
Yeah, of course.
Okay. Why don't you use thermoelectric materials that convert the heat to electricity instead of going through water and a lot of steps? Why don't?
I can tell you the answer to that. It's so there are two answers to this. The first one of which is you can. There's nothing that stops you. So again, this is all going to boil down to economics, right? But if you look at this chart, what I did, which is a little bit difficult to see, but there's a line, which is a yellow line here. It's quite thin, but it basically goes like this. All right. So thermoelectric materials at 100 to 200 degrees that we're talking about. So we're not talking mass, parabolic trough collectors here where you have 300-400 degrees. We're talking low concentration systems. And in these types of technologies that we're using, thermoelectric generators, the best thermoelectric generator available today at the material level, right, is half the efficiency of an ORC system, right?
Okay.
So you end up with an issue where, okay, you might be cheaper, but are you going to be half as cheap? I doubt it. So my opinion is there is a role for everything, right? But for this particular application, if you focus on the low temperatures, thermoelectric generators are not, in terms of their performance, still yet what you can do with conventional cycle technology.
I got it. Thank you.
Thank you. By the way, I should say that shouldn't discourage us. I mean, what it really just means is, okay, let's invest more money and make thermoelectric generators better and better and better. And then one day what I said won't be true, right? And great, then it will be replaced by something else. No problem, great.
Shukri Bilhaj, go ahead, sir.
For your presentation, Dr. Christos. I'm very much interested on the outcome of the experimentation that you talked about at your latest slides. So I hope to read about it or to reach that source of comparison study. It's very interesting. Now, my focus or my question is about your methods dealing with bifacial technology. Has it been studied? Did you look at that? Do you have any idea about? Can you elaborate a little bit about bifacial heat?
Yeah. So it's a very good question, and the honest answer to that is no. We haven't looked at it yet. Okay. We have been studying. So by bifacial, I suspect you mean cells, right? So bifacial cells.
Yes.
Yeah. It hasn't, in my knowledge, it hasn't yet been used in the context of PVT collector technology yet. Yeah. But it's an interesting area, and it's something we have in mind because clearly, as you can see from some of the things I said, we're sort of a little bit gone past the conventional PV cell technology, right? So we've looked at the silicons and the cadmium tellurides and the conventional modules.
Yeah.
And we're now starting to look at, I kind of hinted at it a little bit, but I didn't have a lot of time. I hinted here at maybe going towards, okay, what's the potential of transparent solar cells? So what's the transparent of things like heat cells? Yeah, so it's the same flavor what you're describing, and I think you have a very good point that it would be interesting to have a look at that in this context. Thank you for the comment. It's very useful. Yeah.
Yeah, I just want to add one thing here. In the area where we live here in the Arabian Peninsula, we have two major issues: the heat and the dust.
And the dust, yes.
Both of them hinder the performance of PV systems overall.
Correct.
So anything that could help in actually upgrading performance or gaining energy, but specifically if it does really go in alignment with the economy. Thank you very much.
I want to say thank you. I really like that comment, because it comes from someone from a practical, it's a practical point, which is that it doesn't matter how much theoretically you think your efficiency is. If it doesn't solve real world problems, it's never going to be implemented, or let's say it's going to fall short of the expectations. And I'm going to say one more thing to you, which is that we know this, and we have some ideas about what you could be doing. Let me just say one small thing very quickly.
Okay, go ahead.
So this technology here, you'll note that this isn't what we're looking at, but you'll note that some of the PVT collectors that where is it? Yeah, here, right? Some of the PVT collectors that I mentioned, right? So this is another company's product. This is not us. And if you look at something like this, which is a tube, the concept is maybe you wouldn't expect the same problems that you would if you have a flat panel in terms of dust cycle.
Yes.
So we don't know yet, because no one's tested them. These are very fresh technologies. We don't have years and years of experience in the field to tell you, okay, this is how much it drops because of this and that and so on. But it's let me just tell you that it's not something we're ignoring. We're aware of these problems, and we know that it's a massive issue, and we're trying to think of solutions. Any ideas, right? I mean, I would love to discuss it with you later or by email or whatever. Thank you.
Thanks.
Thank you.
Thank you.
Okay, Hussein. Wahid.
Yes, first of all, thank you for your very enlightening and informative exploration. My question is related to using solar energy for domestic use in Saudi Arabia, whereas we have high radiations, and we have along that available hot temperature, hot water temperature, nearly 45 degrees. So we actually need to cool that also. But what do you think? What is the best configuration to get cooling as well as electricity for such environment and hot weather?
Excellent question, right? So what I'm about to say doesn't apply directly, because you have even hotter conditions than Seville. But Seville is a region which in Europe is close to the highest irradiance. Actually, the highest irradiance, if you look very carefully, is my home country in Europe. So I'm very proud of that. So the closest place in Europe to Saudi Arabia is Cyprus, which I'm very proud about. But in this study, we looked at Seville. So we looked at different types of PVT configurations to see, okay, what's best. Oops, I think I went the wrong way. Yeah, there. So it's a little bit variable, right? And you can have multiple types of solutions for cooling delivery, which I think is really what you're saying, right? On the cooling side, you can either have something, which is driven by electricity. So you can have a so-called vapor compression system, right? Like a heat pump, but it's running in reverse for cooling. Or it's thermally driven. So I showed you one example of a diffusion absorption system, but there are also just conventional absorption chillers, right, that you can buy. And we've done a lot of different, tests for the different technologies. In the very, very hot climates, you start having absorption systems appearing as something of interest, okay? Because there's so much heat that you're generating from this system, and you don't need the heat. You're right. So you're just generating heat and dumping it, yeah? So converting that heat to a useful cooling effect becomes more and more and more promising the hotter the climate gets. So the optimal system switches in terms of, let's say, how do I generate the cooling from something which is electrically driven to something which is thermally driven, the hotter you get. Now, in Saudi Arabia, I can't tell you because we haven't looked at it, but I would love to look at it. And I think it's you know, I hope that the project that we are going to submit with KFUPM for funding there gets funded, because if it gets funded, the whole point of that project is to try to look at, okay, not just the panel. Of course, we want to look at the panel, but ultimately, right, what is the panel doing there, right? Ultimately, it's there to give us this. It's there to cover our needs. So what can we generate from that panel? How much cooling can we generate? And part of that question can only be answered if you say, okay, what's the right configuration? So I don't know whether in Saudi Arabia, the best one will be absorption chillers. But what I can tell you is that as you go hotter and hotter and hotter, absorption becomes really a competitive technology against vapor compression systems. If you go north, it's too expensive. So if you go north, you go definitely towards vapor compression systems. So you just use the electricity generated by the system to drive the compressor, and you run a conventional heat pump in reverse, right? So you're basically just chilling, like the sort of these air conditioning, air source heat pump systems that you run in a cooling mode, right? That you just switch, that you have in Saudi Arabia, quite common in homes.
Okay, Chris, go ahead, sir.
Hello, Dr. Marquitas. I know this is probably outside the scope of your talk, but early on you had mentioned that the cost of nuclear power has gone up. Can you glean any insight on why that's the case?
Oh, what a good question. You don't make it easy for me, do you? But anyway, thanks for the question. I mean, I'm going to go out on a limb, right? I'm not an expert in everything, but I'm going to give you my own view of this.
Sure.
I think these are what you would call added costs. So what we're showing on this plot, and I think this is what you're referring to, right, is
yes.
If you look at the purple or magenta, whatever color that is, line, which kind of goes from about $123 per megawatt hour 10 years ago-ish to, okay, it's a bit old, it's a couple of years old, but so this was, what is it, $150, right? So it's kind of gone up by a good, what is that, almost 20%, almost. Now, why? I don't think it's the, you know, because let me just take one step back, because I think you know what I'm going to say, but for the benefit of everyone on the call. So again, just to remind everyone that what we're showing on this plot is a so-called levelized cost, right? And what is a levelized cost? A levelized cost is not just the money that you spend, right, for building a plant, but it's the money that you spend building the plant plus all of the operating and maintenance expenditure that you have over the lifetime of the plant, and in some cases plus the decommissioning costs, right? So I don't think that the cost has gone up at 20% because the core technology itself cost has gone up at 20%, but I think that due to the fact that you know, safety restrictions, you know, being a little bit more, you know, decommissioning costs going up, you know, there are fewer things you can do with, you can't just, let's just say we are more strict with what happens over the lifetime of a power station than what we were in the past, and this basically just compounds that cost. But I should say I'm at this point just speculating, and to answer your question, I would personally have an interest in reading about if anyone's kind of looked into this. But isn't it curious, right, that it's not even constant? And that's the funny thing, right? It's going up.
Thank you. Thank you. I can look into that for you. This is Chris Lamb, by the way. I was one of your students.
Oh, I didn't hear the surname. Chris, good to talk to you. Yeah,
good.
Fantastic. I remember.
Yes, thank you. And I'm a nuclear safety analyst at Livermore now. So I can definitely look at the safety part for you. And I'll get back to you.
I'm so happy to talk to you, Chris. Yeah, please. I mean, my email is the same as you remember it, right? What's it been, 6-7 years? I don't know, it's a long time ago.
Goodness, it's been a while, but thank you. Thank you kindly.
Thanks a lot. Interesting question. Thank you, Chris.
My pleasure.
Okay, so I think it's late enough. I'll just ask a couple of questions, and I think we can end it. We already are like 1 hour and 15 minutes late. So my couple of questions are: so you showed a figure where you were comparing the efficiency of the solar panels and the PV, actually the photovoltaic and the photovoltaic thermal ones.
Mm-hmm.
And there was around like 40%, around 40% reduction in the efficiency of the PV after you added the low emissivity. Yeah, this one. Yeah.
This one. Okay.
So basically, the efficiency of the PV went down from like around 20, which is usually the number that we would get, down to like 11 or 12%.
Yes.
Take into account that with time, this 11 to 12% will actually decrease more. So the question here is, if we used this thermal energy with an ORC to generate power,
yes,
and the ORC has, like you indicated, it has like 5 to 6% electrical efficiency.
yes,
will that make up for the big loss in electricity?
Yeah,
and
good question. Mm-hmm.
Yeah, so that's my first. So maybe I should leave for you.
Okay, so I'll take that one, and then you can jump in and ask
Exactly.
yourself. But I like the way you're thinking, because these are exactly the things we're looking at from a technical perspective, right? This drop. So let me just kind of clarify what's on this chart, right? First of all, what's on this chart? I mean, PV is simple, because it's just a standard. You can go to any manufacturer. And you can say, okay, what efficiency would I get for a PV panel sitting on the roof, whatever, and you got 18%, whatever. Okay. Now, for a PVT collector, what am I showing? I'm showing a commercial product, right? I'm not showing the best that you could have. And so the question that arises there is, okay, fine, but could you be doing anything beyond just buying a commercial product and telling me, okay, what's the electrical and thermal output of that particular collector? And of course the answer is yes. And you could be doing many things. You could be doing things on the collector level. So you could be, let's say, redesigning the collector in a certain way to be more efficient, which is really going from this solution to the one below it, right? So this solution is just another collector, right, which has been designed differently. Or, and you're right, and I like what you're saying, or you could say, well, okay, look, I just take that collector, but I have all this heat, right? Can I do something with it? Well, of course I can generate some electricity, and what, so on. And the answer is yes, you can. And yes, we've looked at it. And actually, if you design the system correctly, we found that you could even over-generate electricity relative to PV. Okay, you can over-generate electricity. It depends a little bit on where you are, the weather conditions, right? If you are in a hot climate, right? So here's what happens. A lot of these questions depend a little. If you're in a very hot country, let's take Saudi Arabia, right? And you put a PV panel outside on the roof in the summer, right? It's almost impossible for you to get a high efficiency. It gets so hot. And there's nothing cooling it, right? It's just passively cooled, which means that you can reach 60, 70 degrees. There's no chance you're going to be getting anywhere near 18%, okay? And so what happens in those cases is that two things happen. Relative to a PV panel, your relative to a cold climate, the electrical efficiency drops, but also relative to a cold climate, your thermal efficiency increases. So you have all this heat, high temperature, and you can, in some cases, generate even more electricity than a PV panel, right? And then you can say, well, okay, why don't you just do it? Because like everything, right, it is a cost implication. And so someone is always balancing cost and benefit. And someone might say, okay, yeah, sure, I want to generate more electricity, right? And I don't care about the cost, right? It's a little bit like buying an expensive car. Yeah, I can buy expensive car. I can afford it. I like it, yeah? Or you can say, I don't. And it's kind of like, it gets down to basically just different products and options, and then different users make different decisions. Some of them are rational and some of them are irrational. I don't know if that makes any sense, but as you say, there are many options.
Just as a follow-up question to the first question, that's not the second question.
Yes.
What is the temperature of the water that gets heated?
In this chart, 60%.
In general, in your calculations, it's like
in these calculations, 60 degrees Celsius, and in general, what you want is to be heating water above 50 degrees. Because hot water, basically, you have salmonella issues, and so there are regulations. There are different regulations in different countries, but at least for short periods, you need to be running it over 60 degrees. So when we're doing this comparison in this chart, by the way, this is a modeling comparison, but I can show you how the experiments actually verify this. This is at 60 degrees. So this is with the panel at 60 degrees, not for the PV, right, but for the PVT.
So basically, you can't use it for an absorption refrigeration cycle. This absorption would require higher temperature.
At this condition, no. But if you run it hotter, you can.
Okay. My second question is in the diffusion absorption refrigeration. That was actually so interesting. I just realized that you had hydrogen in the game.
Yes.
With ammonia and water.
Yes. That's
Why
right.
is that?
Let me see. Where did I show it? So yes. So this is what you're saying, right?
Yeah.
Right. So a conventional absorption refrigeration or chiller, right? People call it an absorption chiller. Yeah. Is just ammonia water, right? So you use ammonia water. You pump these things around, and you use absorption processes, right? Physical process to absorb and release heat at different temperatures, which is what gives you your cooling effect, right? Now, what happens in these cases is that unlike an absorption refrigeration system, conventional one, here you don't have a pump. Now, what does the pump do? Well, the pump creates a sort of a pressure difference, okay, which is what allows you to have a temperature difference, okay? So here, what you actually do is you use the hydrogen to create an atmosphere of low reduced pressure where ammonia evaporates into the hydrogen, okay? So what really happens in this type of system is that there's a part of the system, which is really this thing here. It's this snake part, right? So this part over here, which is the cooling part, at the top of the unit, where the hydrogen, because it's a light molecule, collects at the top. And what happens in that particular unit is the ammonia evaporates inside a hydrogen environment, okay? And that's what basically generates a cooling effect. In fact, this thing can go -20. Okay, so the hydrogen is there to replace, if you like, so to create the pressure difference, which is not a real pressure difference, it's a reduced pressure difference, okay, instead of a pump, instead of a mechanically driven pump.
Okay, did you try these systems with hydrogen systems, like with water splitting? No, yeah. I mean in general, the PV thermal. Did you try incorporating these into like water splitting systems for hydrogen?
Oh, you mean to integrate this with the PVT?
Yeah.
No, not yet, not yet. So we've tried them, but we've been mainly driving them with conventional solar collectors. So these are not PVT collectors, right? These are conventional solar thermal collectors. There is a challenge in driving these with PVT collectors, but I think really that's what we're trying, that's what we're heading for, right? So we have one technology which is being developed separately. Let's call it solar cooling, which is based on the DAR. We have another technology which is about the collection of sunlight, which is the PVT. And the point of what we're discussing here is, maybe soon we'll be able to integrate the two, right? So instead of having here your conventional, right, vacuum tube solar collectors, you'll have a PVT collector, plus the electricity.
Perfect. Okay, thank you everyone for this, for attending tonight, and thank you so much, Professor Markides, for this very nice presentation. And yeah, so I hope everyone has a good night.
And thank you very much. Good night, everyone. Thank you.
Thank you.
Good night. Bye-bye. Have a nice night. Thank you very much.
You too. Bye-bye.